So today I'm going to talk about many things. I'm not going to be able to finish, so I can just as well just fly over various topics, but mainly related to the K framework, which is a programming language framework built on the following vision. So we believe that it is possible to have one formal definition of a programming language, and only one. And then from that one definition to derive all the tools that you need for your language, including deductive program verifiers, model checkers, even compilers and interpreters, debuggers. So all of them to work not only in principle, but to be the right way to develop these tools. I know that many of us believe that we already have it, and I'm going to just show you our journey. There are many different ways possible, but what is important for me at the beginning to make it clear that everything we do is fueled by this firm belief that this is possible. For example, I will never ever spend time, me or my group or with my collaborators, defining the same programming language twice in two different formalisms, because I don't think that is necessary. And I know that's a strong claim, and I may make a few others, but just for the sake of having an entertaining discussion, I'm going to just say it. As I said, I'm going to tell you the K framework story. There could be other parallel stories following the same beliefs. So the way we develop the K framework, I'm not saying that we already solved that problem. I'm saying that this is our approach to it. And everything we do is fueled by this belief. So the K framework started about 15, 20 years ago when we tried to formalize programming languages in various styles. And then trying to use these different formalizations to define actual real languages. Not only toy languages like IMP or FUN, but to define actual real large languages. And one thing which was very hard to do, but we had to do it, was to refrain ourselves from coming up with a mathematics for it. I love mathematics. I've done mathematics all my life, and I continue to do mathematics. But I thought that that's not the right approach to design the framework. What we should do instead, we should use it, we should engineer it. We should define real large languages, see where we hit walls, and learn from there, and then design the mathematics underneath. And one thing we learned, and I'm sure that many people in the room learn the same thing on various occasions, is that if something works, then it will also have a nice, beautiful mathematics with it. So let's make it work first, and then let's worry about the mathematics. So that was the approach. And before I jump into more details, I'd like to give you a very high-level flavor of K, in case you haven't seen anything before like that. But whatever you see here will be very familiar because it borrowed ideas from all frameworks. I'm not going to mention them, but you will see all these ideas from various frameworks here. What you see here is what we call a language poster. It's generated automatically by one of the K tools from an actual textual definition. And what we have here is syntax and macros on the left, and then the other two columns define semantics. And I'm going to zoom a bit just to give you a flavor of it. So syntax, we define syntax using conventional BNF notation. However, pushed by users of the framework defining real languages, we decided to annotate the syntax with all kinds of annotations like this. For example, this says that assignment, this is a C-like language, kernel C. Assignment is strict in the second argument, meaning that you first evaluate the second argument, and then we worry about the semantics of the assignment itself. So it turned out that it's a lot more convenient to add all these evaluation strategy annotations, which are pretty clear when you define your syntax of the language, at the same place where you define the syntax. Users complained repeatedly when they had to define the syntax in one place and then go somewhere else to define the evaluation strategies, because typically they go hand in hand. So we developed a whole collection of notations like this. This is not the only one. There are many others that you annotate the syntax, and they immediately have semantic counterparts, but you don't have to worry about defining those yourself. Then you need a program configuration, and the approach to define program configurations in K is like in the chemical abstract machine. In some sense, you have a solution where the various semantic components, they are called molecules in the chemical abstract machine, we call them cells here. They have names, the various cells, and they hold semantic information. And you can think of them metaphorically, all these semantic components float around, you just mesh them whenever you need them, they are there, just grab them when you need them. And you don't have to mention them if you don't need them. So in this case, this language is so trivial, you only have a few semantic components in the configuration, like the program continuation, whatever is rest to is to be executed. functions, environment map, memory heap, function stack, input-output buffers, a pointer map, and so on. So again, it's a very simple language. And finally, rules are the main semantic ingredient of the framework. And they are rewrite rules in principle. But as you can see, there are some slight modifications to rewrite rules as we know them. In particular, what we call local rewriting. So see, this rewrite rule has two arrows. This is the semantics of assignment. Remember, assignment was strict in the second argument. So the second argument became a value. This is how you write it in ASCII. This is what the PDF generator generates. And what you say here is that for the assignment, where this is a value now, because it was strict in the second argument, the assignment in C rewrites to the value. And in the environment, you have to bind X. So X must be declared. And this is the binding of X. And whatever is there, it gets rewritten to V. So there are two rewrite relations. And because you localize rewriting to where it actually happens, again, that was a big push from users. Because initially, we used normal rewrite systems where you have a whole configuration writes to a whole configuration. And 95% of the configuration was the same, unchanged. So there were lots of opportunities for mistakes, typos, and so on. They said, I don't want to write things that just repeat. So introduce this notation, ... Literally, you have to type the 3 characters, ... in the rule, which we call structural frames, and they stay for the context. That doesn't change, but you don't care about. Since you don't care about it, you don't mention it, but you still say that there is some context there, ... If you don't put ... it means that the assignment is the only assignment in the cell. But ... it means that there are more. It's a context. And here the assignment writes to V, and at the same time, whatever X was bound to writes to V. So this is how you write the rules. And we paid a lot of effort on designing the notation so that you don't write anything that you don't need, basically, in a rule. Everything can be inferred, including the context in which you apply the actual transformations. You can think of K rules as transactions because they match what they need in the configuration, and they write some of the parts only. It's very easy to translate this to any other formalism. For example, top-level rewrite rules, you just have to add additional variables. So that's not the hard part. The hard part is to go the other way around, to come up with the right notation that people are willing to use. People who sit down, the semantics engineers who sit down and spend 2 years from their lives to define a language like C, they are willing to use and not yell at you too often. So that's how K looks like. And actually, most of the complaints that we got from users is about syntax. They don't like the syntax. Like, many complain, why did you pick this XML-like notation? It's so ugly. Well, so you need some notation for cells. So now I experiment with different syntaxes. And you can actually define your own syntax now, even for K. And what K does, it takes the syntax of your programming language and its own syntax and mixes them, generates a parser that then will be used to parse the right rules and semantic components and programs and everything. Right. And you may have ambiguity, so there are lots of things under the hood, which I'm not going to get into. But as I said, the whole effort was driven mainly by defining real languages, like JavaScript, Java 1.4, x86, we just finished it, C11, and now several other languages in the blockchain space. When I said that the effort was driven by defining these languages, the stated goal from the very beginning was to define these languages completely. Not a convenient fragment, enough to write a paper, not even 95% or 99%, but completely. And what does that mean is that you take benchmarks of programs that people use to test their implementations, interpreters, compilers, and so on, and be able to handle all those benchmarks with the semantics. Right? So only then you have confidence that you have the whole language. All right. Some languages can have huge configurations. This is the configuration of C, for example. It has more than 120 semantic cells grouped on various levels of nesting, and it has more than 5,000 semantic rules. All right, so next, I'd like to go into some detail. So far I showed you the yellow box, some detail in the blue boxes, and I'll focus mostly on verification and deduction. But before that, I'd like to discuss a bit the interpreter, because this is one of the most used tools, which was under continuous improvements. There is a huge need to get these semantics and generate fast execution engines for them. So that's one of the most pressing user requests. Make it fast. And I'm not going to tell you how we implement it. I'm going to give you some numbers later. So the way we do it at a high level, we take the K definition and compile it into an LLVM program. And then we use the LLVM compiler to get native code. We used to go through a camel, but now we switch to LLVM for more performance. Right, so this is how it works at a high level. And currently, one of the tools in my company called RVMatch is powered by this. It's called RVMatch. Is basically a syntax of it's the semantics of C plugged into the LLVM backend of K. So you take C programs and run them with the semantics. It's a dynamic checker based entirely on the semantics of C. It can also be used for symbolic execution, but in the commercial version of the tool, we only use it for dynamic analysis. It's an undefined behavior detector, basically. Because we define completely all the undefined behavior of C in the semantics, and now if you take C programs and run them with the semantics, you catch the undefined behavior. So you take programs like this, and normally when you run them with GCC, you compile them, get a binary, run, nothing happens. But this program has a problem, and it doesn't matter really what problem it has. When you run it with the RVMatch tool, specifically with the KCC tool, part of the RVMatch toolkit, you have exactly the same experience as a user as you have with GCC. We spent actually a lot of time trying to make it very easy to use. Initially, as you can imagine, it was complicated to use. We had to compile the semantics first, then link the program, parse it, and so on. And we lost lots of users because of that. So we actually spent a lot of time in the company thinking how we can make it really easy to use. And somebody came up with the idea, let's make it one character learning curve. And okay, let's do that. And then we wrapped everything into a tool called KCC. And if you're a C programmer, you think of it just as a drop-in replacement of GCC. But what happens under the hood is that the program is actually executed with the semantics generated from, with the interpreter generated from the semantics. And when you run your program, you get errors like this, which are pretty useful to developers. Also pointers in the C standard, you can click on those and takes us to the C standard showing you why the behavior is undefined. And this is good enough to be used by several companies, actually in terms of performance. I'll give you numbers later on. We worked with customers in the embedded and mission critical space. And now what we've done recently, very recently, 2 years ago, we started using exactly the same backend, the same technology, but with blockchain languages. And this way we get actually implementations of blockchain programs that, programming languages that can run smart contracts. And you can actually power the entire blockchain with semantics, basically. And I'm going to give you some details about that later. But for now, I'd like to go a bit into how we do other things, like verification. If you have any questions so far, I'd be glad to take them. Yes. So C is a very bad example for me because C is so well engineered. Just, you know that the LLVM has an interpreter, and an interpreter is 1,000 times or more slower than the actual native compiler. So we are in the same range, actually even worse. We are about 10,000 to 100,000 times slower than the native code. But in the blockchain space, I'll show you numbers. We actually outperform some ad hoc manual implementations already. All right, good question. Right, so let me tell you a bit how we do verification, because that's really interesting. I mean, the most interesting part, I think, for you. Again, keep in mind that we use exactly the same definition. So the exact same semantic that is used to generate interpreters and tools and so on to run programs is used for verification without touching a single character in the semantics. So how can you do that? How can you use that for verification and effective verification? So first, the state of the art, when we talk about verification, is to take an operational semantics and most of the time discard it because it's not meant to be used for verification. We need to define the language differently as a separation logic, or as an axiomatic semantics, a Hoare logic, and then we can add proof rules like this, for example. These are the proof rules for while loop invariants or for recursive procedures in a Hoare logic style. It doesn't matter, I just picked Hoare logic, but in other formats you have to do the same. So you have to rethink your language. You have to sit down and rethink your language. And when you have a language like C with 5,000 or more rules, that's a very serious endeavor. It may take more than a whole PhD, maybe a PhD for 2 people or so. So it's a huge effort. So we'd like to avoid that. But how can we avoid it? Because on the other hand, Hoare logic is really nice because it gives you the exact proof rules that allow you to prove properties about programs. So what we'd like something like Hoare logic, but to be completely language independent. Something that gives you, takes an operational semantics as a theory, as axioms, and allows you to do reasoning about that, which is as nice and useful as with a Hoare logic environment. So we like to be able to derive any properties from the operational semantics, and at the same time, we want everything. Let's also aim for a sound and relatively complete proving procedure because we generate it from the operational semantics directly. And I think the key insight here is that we like to do all this elegantly and naturally and efficiently, right? Because it can be done in principle. In principle, you can take an operational semantics and use inductive proofs, using induction, use all kind of automation, and you can do things in principle. But we'd like to do it at the same level of elegance as you do it with other logics, specifically crafted for reasoning about programs. And if you now shift a bit focus from programming languages to logics, right, we use various logics in the community, various logics to specify properties about programs, like first-order logics, horror logics, separation logics. Then we have temporal logics, like model mu logics, CTL, LTL, LTL star. We also have equational logics, various types of many sorted order, sorted algebras, also dependent types, type systems. So there are definitely various approaches that we use to write properties. So if we want to come up with a logic that allows us to reason about any programs in any programming languages, we should also look at the foundational aspects of it. We should look at the logics and try to come up with a logic in which we can somehow reason about these logics. And more specifically, what we'd like is to have a way to define or to reason about other logics at the core level, not at the meta level, right? So we'd like to be able to have a theory, for example, in this logic that corresponds to linear temporal logic or to CTL, and then to use the generic reasoning mechanism to reason about CTL or LTL. Well, is that possible? We don't know. It's still a search, but I will tell you what we have so far, and so far it explains everything we need in the K framework. There could be limitations, obviously, like with everything else, but we'll see those when we get there. To give you a high-level overview, we call this logic matching mu logic. And in my view, it's a very simple logic. But when you say that something is simple, it's typically a biased opinion, subjective opinion. I fully understand that. But I believe it's really simple in the sense that the syntax, it has only 7 syntactic constructs. The semantics has 16 proof roots in total. And you can reason about first-order logic, least fixed points, framing with the logic. And the proof checker, probably that could be a bit more interesting for CPP. The proof checker itself has only 200 or so lines of code. Of course, depends on how you count, but the point is it's a small proof checker. And we have 3 draft proof checkers, 3 prototypes in 3 different languages, and all of them are pretty much within the same range. So in this logic, the formulae of the logic, to prepare you for the next slides, we call them patterns, and they are not terms, they are not predicates, they are not functions, they are patterns. And we can regain terms and predicates and functions axiomatically. If we add some axioms to patterns, then we get terms as we know them. If we add some other axioms, we get predicates or we get functions. So, and that was important for K, because in K, it was always difficult to say what is a function, what is a predicate, because in the end, it's all pattern matching. So the semantics will be pattern matching, and the syntax will be that of patterns. So this is the syntax. So suppose that you have a signature, a many-sorted signature for now, sigma, and then you have symbols. We call these symbols because they are not really operation symbols, they are not interpreted as functions, you see. We call them symbols. And what you can do for each sort, you can build patterns, phi s, all the patterns of that sort. And we have different types of variables. We have 2 types of variables. We have element variables and and set variables. The difference is that the element variables are matched by precisely 1 element in models. The set variables are matched by a set of elements. Then once you have patterns, you can put sigma symbols on top of them. So you can build bigger patterns from smaller patterns. And again, the semantics of patterns is that of pattern matching, which means that you can also go. So what we have so far here is like normal terms with these 2 distinct kind of variables. But you can go further and actually do logical reasoning with patterns. You can very well conjunct 2 patterns. So the semantics of this is intersection. If you have to match a conjunction of 2 patterns, you have to match each of the patterns. You can have negation. You match not phi if you do not match phi. And the interesting construct are the binders. you need some way to, so this allows us to reason about structure, this allows us to reason about logical constraints, but at some point you need binders of some sort. You need one or another to deal with binders. And we've been through various waves of beliefs, what would be better as a binder. And in the end, we decided to stick to a simple existential pattern, existential binder, but you can only quantify existentially over element variables, not over set variables. And for least fixed points, we added a mu binder, which you can only bind over set variables. Right, so that's the syntax. And the semantics, it's almost like first order logic, except that the symbols are interpreted not as functions in models, but as functions in the power domains. Or in other words, they're interpreted as relations. And the intuition is again that of matching. So if you give me sigma, if you give me a pattern in the model, that will be matched by a set of elements. Because when you do matching, you can be matched by various things. Like in K, if you have a configuration pattern, that can be matched by lots of concrete configurations, not only by one. All right? Oh, yes.
So a difference from patterns as we're used to them in, say, ML is that you don't bind variables that are then available somewhere else. Is that right?
You don't bind element variables. With mu, you mean?
In general, like in ML, a pattern, the whole point of it is,
Yeah.
is to populate a variable environment with names for subterms. That part is not present here. Is that right?
I mean, you can have these symbols, which can be top-level symbols, right? And those are like constants. Constants, for example, can be symbols. And then, yes, I don't understand exactly what you mean.
I got stuck. It seemed like you were saying the meaning of a pattern is which terms it matches against.
In the model. If you give me a model, then you have a meaning, which is the set of elements that match it. Yes. And the existential, so this is actually the union over all possible concrete matches of Z. Right? So gives you a set of all the elements that match. It's an abstraction.
We care not just about which terms in the model match, but also how we wind up figuring out the values of all those x's, right?
The substitutions, how you get the matching.
Isn't that part of the semantics of a pattern also?
Well, so there is a valuation when you define the semantics, yes. So yeah, the semantics is all those values of the variables. So you have the values, and then additionally, you also have multiple elements that can match. So once you have an instance of all the variables, you can still have a whole bunch of elements that match. Not like a substitution gives you a unique matching. Okay, thank you. All right. So now we can define the usual derived constructs, like disjunction, implication, if and only if. It's very easy and natural to think of patterns as sets. Right, so all the set, all the elements that match it. And then they have a diagrammatic representation like this. For example, implication are all the elements that whenever they match phi 1, they also match phi 2, so all the gray area. What is probably a bit unusual is that you can write things like this in matching logic, which is exists x, x. And you can do that for every sort. Okay? And that is the truth, basically, saying that semantically it says that the carrier is the union of all its elements, which is obvious. We need to add that to the proof system to be able to reason. But you can do that. You can quantify over any patterns, not only over predicates. I can quantify over a variable. And you can also define largest fixed points. And by the way, all these have been already presented in other papers. So here I just want to give you an overview so I can get to the interesting part of the presentation. And I have to really go faster. Now it's so the syntax is very poor, but that was the exact point of the whole effort here, because we believe that we can regain everything we need axiomatically. We can add symbols, we can define theories. I can add some symbols and some axioms, and I can get what I want. In particular, this is a very important symbol we call the defineness symbol that allows you to take, so you see the truth now maybe, so empty means typically false, the total set means absolute truth, but then you can have lots of other valuations in between. But we still want sometimes to use to reason binary, something is either true or false. And then we would like to be able to take something which is not entirely true and turn it into true unless it is already false. And this is like the ceiling, we call this the ceiling operator, or the defined symbol, which is just a symbol, and it has an axiom like this. And the effect is that if you take any pattern and put it in this ceiling bracket, that will become either the total set or the empty set, depending on whether phi is defined or not. If phi has anything that matches it, then you'll get absolute truth. And you can move truth from any universe of any sort into any other universe. And then dually, you can define the totality operator, which is empty if and only if phi is not top. And once you have that, and again, I just added one symbol and one axiom, so it's a theory in matching logic, very simple finite theory. Then you can define lots of other constructs which are very useful, like membership, inclusion, even equality. Okay? So membership for a variable, it's a set variable, an element variable belongs to a pattern, meaning that I will match that pattern, X matches that pattern. But what's really interesting is that you can define equality. In first order logic, you cannot define equality in the sense that we cannot add axioms so that the models will be exactly the models where the binary relation is depicted as equality. It will be some isomorphism. But here you can define the exact equality, and it's defined like this. You basically say that if you take the if and only if is the complement of the semantic difference, that should be empty. And I put the totality around. All right? So we regain things that are very useful. Also functions. We don't have functions yet, so we wonder, how can I define a function? So a function can be defined now in a very naive way. You say that there exists a y such that x of sigma of x1, xn is y. Right? Because y is a set, it's an element variable be interpreted as a singleton. Right? So that's saying that sigma will be interpreted as a singleton. It's a total function. And actually in K and on paper, we write them exactly this way, but this is just sugar for this axiom. And similarly, you can define partial functions, total relations, and modulo some simple syntactic sugar notation. You regain the actual usual way to write axioms and define models. Yes. Please don't ask a hard question. Because y, in all models, y, so that's an element variable. The element variables are interpreted as singletons. I didn't show that on the slides. The element variables are interpreted as singletons. Sigma will be interpreted into a power set, but being a y here and exists y, it will be exactly one element. We don't know exactly which element, but it will be exactly one. And if you want to define a partial function, you say here implies y, meaning that's included in y. All right. What could be more interesting is that you can define actually term algebras, and this way initial models, up to an isomorphism, not up to elementary equivalence, up exactly. You can define the exact model. And you can use mu here. So suppose that you have some constructors, and you want to define, let's say, natural numbers over those constructors, zero and successor, or lists over nil and cons. So you can use mu, and it's a very simple definition. You just say mu, and D is a set now, a set variable. Remember, mu only binds set variables. Mu D, and then the construct, all the disjunction for all the constructors, basically. So in the case of natural numbers, this defines exactly the natural number. They say mu n is a set variable, 0 or successor of n. Okay, so that defines the list set n such that 0 is in it, and successor of the whole set is also in it. And that's the natural numbers. Or the set of all lists, once you have natural numbers, you can define then list over natural numbers, like mu L, nil, or cons of, and this is the total set. This contains all the natural numbers, and L is the same L that is bound here. And you can prove that these are the exact models, the initial models, which tells us in particular that we are not going to have a complete proof system, right? Because you can define exactly natural numbers. Separation logic is another logic you can define as a theory. Separation logic really ends up being matching logic over a theory of maps. You can define maps, symbols like the binder, the merging operator. Then you define list, which is separation logic is a predicate, now becomes a symbol, but will be interpreted as a set of all the actual linked lists that will match the list pattern. And what you see here is exactly matching logic syntax. but it looks like separation logic syntax, and that's the whole point. Right, so it's in this theory, match logic of maps, you can define these things. And you don't even need actually to see for this, you don't even need to say the least fixed point. You can define also the least fixed point. It happens that in the model of maps, it's exactly the least fixed point, a finite domain maps. And then using the matching logic proof system, which I didn't show you yet, yes? So we do not quantify over higher order things, but we do define higher order things. I think that's a longer discussion. We can define sorts, which are sorts of function sorts. If you give me two sorts, S1, S2, I can define a sort for the functions from S1, S2, S2. And then I can quantify over that. But I would rather get into that discussion offline, because that's tricky. I love to talk about this, but it's tricky. And we can talk offline. As I said, this already published somewhere else. I'm just trying to give you an overview so I can move to the interesting part. Now using the matching logic proof system, which I haven't showed you yet, but I'll show you on the next slide, you can do reasoning like this. You can start with a heap, let which is like this, and doing reasoning, equational reasoning and implication, you get this, so implies this list, meaning that this is a particular, you can think of it in models, this is a particular heap that matches this predicate, this pattern, actually, we don't even call it predicate. And then framing comes basically for free. You can take this reasoning and you can put it in any configuration pattern. So if I want to do the reasoning in the heap and I have a more complex configuration, I can just do the reasoning there. And that's thanks to a proof rule that I'm going to show you on the next slide called framing. Here it is. This is the match logic proof system. It includes standard first order logic reasoning. It turns out that the patterns can be regarded as, from a reasoning perspective, as predicates. So all the proof rules of first order logic happen to be sound, exactly for patterns as are, which was, for me, it was a bit unexpected. I didn't expect that, but it turned out that they're exactly sound. Then you need to think about propagation now, because you can put symbols on top of logical connectives, like in modal logic, for example. You need to worry about how does reasoning under these symbols propagates. And it turns out that some reasoning propagates, other types of reasoning propagates, others don't. In particular, things related to case analysis, they propagate. So if I have a symbol context, this is a sigma, and I go to some of its arguments, then bottom is propagated, disjunction is propagated, meaning that I can do case analysis locally. Also, extension quantifiers propagate. I can move an extension quantifier from here above. And this is also related to Baran's, I think, proof rule in modal logics. And framing, meaning that if you prove an implication locally, you can lift it. Right? And this is what allows us to do reasoning in the heap locally and move it up, or in stacks and move it up.
But this doesn't seem to be the same thing as the frame rule in separation logic. It's sort of...
It's framing statically. In separation logic, you do it dynamically. You do a few steps. And then if you have additional constraints, like you don't modify certain things, then you can still prove that as a lemma, based on using fixed points, for reachability and so on. But yes, it's not exactly the same. But it's framing locally in the statically. All right, there are these two technical rules, which are really unexpected, but they had to be there for proving completeness of some sort of the logic, because, as I said, the logic cannot be complete in general. In particular, exists XX that cannot be proved. You have to assume it. And then reasoning rules for least fixed points, which are pretty expected. You have a prefix point saying that mu is a prefix point, and then the Knaster-Tarski, also called the Park rule, borrowed from modal mu logic, which says that mu is really the least fixed point. So if you give me a fixed point psi, then mu is smaller. All right, so let's go now closer to K. So you can define transition systems pretty easily. All you have to do is to define a symbol. That's it. You define a signature with a sort, let's say state and a symbol. And that symbol will be interpreted as a set anyway, so that's the transition relation that you need. So one symbol, you get transition systems. And the intuition here is that that symbol applied to phi next, we think of it like one path next. Phi means that I can go from here in one path to something where phi holds. Okay, so basically you are here and phi holds the next state. So one symbol and one sort, you got transition systems. Once you have that, you can define then all paths next. If you think of this bullet as one path next, then all paths next will be the dual, like this. It is not the case that on one path, not phi. Diagrammatically, it looks like this. So from all path phi, you only go into things that are in phi, but you may also get stuck there. And then you can define using mu the usual friends, like eventually, always, strong until. Also, you can define well-foundedness. You can say mu x on all paths x. This actually, if you add it as an axiom, it means that you only mean finite paths. Okay. And we can now capture logics like LTL, CTL, CTL star, which are very important for particularly in the context of model checking, but not only. They become theories in this matching logic signature. And basically, they are combinations of these three axioms. It just happens to be of these three axioms. Like inf that says next t, meaning that you go infinitely. At every moment, you can go next somewhere. This says that you have finite traces only. And lin, that means that you have linear traces. Says on one path x means on all paths x. Right? So that imposes linearity. And now you can get the various other logics as theories combining these axioms. But more importantly to K is that rewriting or reachability claims can be seen also as now statements in matching logic. And why is that important? First of all, because that's what K really does. It proves such reachability claims. Second, because whole logic triples, like pre-post condition, they can be seen as reachability claims, where you start with a configuration containing the code and the precondition, and go to a configuration where the code is empty and the post condition. This is a partial correctness argument, reachability logic, meaning that if the program terminates, then you get phi prime is matched. And that can be also expressed now in matching logic as a formula, as a pattern. How about completeness? Completeness, as you expect, doesn't hold in general. And we work hard to identify fragments on which it is complete, because we'd like to get the completeness results or disability results of other logics from this general result. And we still want to do that. It's hard. We managed to prove the completeness only when we have defineness around, because we can define equality and then we can translate to first order logic with equality. But we were not able to prove it in general if we don't have defineness. We only proved it for an empty theory, which is called also local completeness in model logics. We conjectured it should hold for all theories. So that's what happens if you get rid of the mu binder. If you get rid of the existential binder, we know that we cannot be complete in general, so we have to get rid of something. If we get rid of the existential binder, then we only have conjectures, unfortunately. You know that for model mu logic, there's an open problem whether we can the proof system proposed by Kozen was complete or not. Took almost 10 or 20 years to prove it. Igor Valukiewicz and collaborators managed to prove it. So this generalizes that setting, right? You have these sigmas, which can be seen as polyadic model operators. And we are working actually with Igor to prove this result. We believe this is true, but we don't know yet. So it would be really nice to have a proof for it. And for full matching logic, we believe that we almost have a proof that we can get completeness if we work with Henkin models, which is a bit of cheating, but at least gives you confidence that your proof system is complete, is good enough. Okay, from some point of view. All right, so we wanted this logic. We have something which is good enough for us. Right now, I'm not saying it answers all the questions, but it's good enough. And I didn't show you at all this part here, which is not yet published, but I will be glad to give you some drafts. What is K? So K really is the best effort implementation of this logic. But K was first, then the logic came. And the logic found new ways to look at things, and now K tries to catch up with those new ways to look at things. From the outside, the K prover, K program verifier, is like any other program verifier, where you take a program and a specification and it proves it. What is different is what happens internally. Internally, you have the verification infrastructure, which is completely generic, completely language independent, and you plug and play your language semantics, and you get the same degree of automation when you do verification as you get with tools like Boogie or VCC where you don't have to interactively do the proof. You can, the logic allows you to do that, but we try to be as automated as verifiers like VCC. And to move to the blockchain, all you have to do is to plug and play different languages. And in terms of performance, I would like you to not worry about performance. We've done lots of experiments, and we are very comparable in terms of performance to provers like VCC and others, because the time goes to prove things here. So what K does, the prover does, is to take programming language out of the picture, and then you focus on the hard problems, which is to solve all these domain constraints. That's how properties look like in K, because, as I said, this is language independent, so you may wonder, how can you write a property about a program in a language independent way? Like any other rule. So this is, for example, the semantics of a while loop, for an invariant of a while loop in a sum program. And as you can see, we say that the program rewrites to nothing. In a context, I may have more stuff in the K cell. And in the state, the program variable n, which is a constant, is bound to a mathematical variable n, which eventually writes to 0 when the program terminates, because the counter decrements. And sum is sum s, and at the end of the loop will be this thing. Okay? And now you can just pass it to the prover, it will prove it. A couple of seconds or whatever it takes. And you need also some side condition n larger than 0. And everything it does under the hood can be explained in terms of machine logic reasoning. For the blockchain, we plug a blockchain language. And we started with the EVM, which is the Ethereum Virtual Machine language. Most of the smart contracts these days are executing using the Ethereum Virtual Machine. And fortunately, the designers of the EVM did a very good job. They have a C++ implementation that comes with 60,000 tests, which is great. Why? Because it's extremely important for the various blockchain nodes to agree on computations, because they have to redo the computation, they have to agree. If they don't agree, there is a major problem. So it's very important to make sure they all have the same implementation, or correct implementation. So they have all these tests, and by default, they think that any client that passes all the tests is correct. So that was very good for us, because we took all these tests, generated an interpreter from the semantics, and then ran all the tests. So we passed all of them. What was surprising, in a nice way, was that the interpreter that we generated using the LLVM backend was actually 25% faster than some ad hoc implementations of the Ethereum virtual machine. Some of them very, very intensively used. Probably the most used implementation of EVM is the one written in JavaScript, part of Truffle. Truffle is an IDE where you develop smart contracts. Right? So each time you have a smart contract to test it, you have to compile and run it with Truffle. And Truffle runs a simulator of Ethereum in JavaScript. Okay? So we made the semantics pluggable in Truffle. So now we're working with Truffle to actually switch that JavaScript implementation with the actual generated, semantic-generated semantics. We do not beat yet the C++ implementation. And I say yet, why? There is a C++ implementation of Ethereum, which is widely used. Why? Because they didn't, when we talked to the designers, Greg, Colvin, and others, they said that they didn't spend a lot of time to make it efficient, because that was not the point. The point was to be very clear so people understand it, so it serves as a reference model. Great, and the semantics is even better from that point of view. But so we hope that eventually we'll also be able to catch that. So like 2 months ago, we were like 10 times slower than the C++. So there are lots of progress being made. We had an OCaml backend previously to K. Now we have an LLVM backend, which is a bit faster. And we collaborate very closely with the Ethereum Foundation, and many people in the Ethereum community use these semantics now as the canonical specification of the language, not the yellow paper that introduced the EVM. They use this KVM semantics as the canonical one. And there's a lot of pressure to actually generate human-readable semantics. So now we generate a website called jellopaper.org, completely automatically from the semantics. The semantics in literary programming style written. So we generate this, which is completely human-readable, generated from the semantics. At some moment, you have to run into rules like this, but people said that after an hour or two of reading, they get used to it. It's not a huge effort. But more importantly, you can actually generate from the exact same semantics used as documentation. So semantics is documentation. It's the best possible documentation. Right? But you can also generate interpreters from it, which are fast enough that some companies actually, like Cardano, IOHK, started a testnet based on these semantics. So it allowed users of smart contracts to run their smart contracts on a testnet that was powered by a VM generated completely automatically, right, from the semantics. And nobody complained about performance, actually. It was never a complaint. We had some bugs, but nobody complained about performance, which was nice. And there is a tool also we developed in our company, an RV match-like tool, but for smart contracts called Firefly, which is, again, generated completely from the semantics the same way. But more importantly, and where most of the revenue in a runtime verification company comes from, is from formal verification of smart contracts. So customers approach us and they say, hey, I have this smart contract, I believe it is correct, that's what it does, and then we have to formalize it and verify it. And we use, again, the exact same semantics. And we work very closely, as I mentioned, with Ethereum Foundation, because we have a good relationship with them. They also gave us the first security contract to verify Casper, which was a tricky program written in EVM initially. In Viper compiled to Solidity, compiled to EVM, and then executed. And the compiler had bugs. Nobody trusted the compiler, so we had to verify directly the bytecode. All right. In order to write properties, you have to also formalize specifications. The good news in the blockchain world is that many smart contracts follow certain templates, and people don't deviate too much from these templates. And templates like you have to transfer money from point A to point B. There is a very clear thing to do there. You may have some slight variations, but the main thing is almost the same, which is great for us as a formal verification community because we can literally sit down and formalize all these standards. They are called ERC20, ERC777, and many others. So we formalized all those, and we use them now to verify smart contracts. So smart contracts written in this binary format. You take the semantics and verify that they satisfy these specifications. And the process is pretty tedious, but we expect it. You take English like this, the so-called business logic of the standard token. Then you formalize it, and in case it looks like this, for example, it's a transfer function. Transfer succeeds from the current account, which is the caller, F, from. You match your balance, rewrite it to balance minus V, you transfer V. Right? You go to the 2 and increment the balance there. You also log the event, and there are some side conditions that you need to satisfy. This is a K rule, exactly the same kind of rules that I used to define semantics. So exactly the same rules, you write properties in them, and they're executable too. Right? And then you take the binary, and there is a translation process. You have to translate this to the bytecode level, and this is semi-automatic, unfortunately, yet. We like to automate it completely. Yeah, so you get this ugly from this beautiful, but that's life currently. And we verified several important smart contracts in the Ethereum blockchain community, like the ETH 2.0 deposit, which allows you to move money or tokens from Ethereum 1 to Ethereum 2, which will come hopefully soon. A multi-signature, this is an exchange, and so on and so forth. So these were like multi-month, man-month efforts, but they only need the semantics. What is really nice is not to take an existing language and formalize it post-mortem, but to design new languages directly this way. Right? So why should we always implement languages in an ad hoc way and then come up with the semantics? It's a great opportunity now that we can change things. Let's define languages directly through their semantics. They design languages by defining them in formal semantics. And by the way, in case you wonder, that's how Ethereum contracts look like. That's what you have on the blockchain. That's what you trust with your money. Right? So you call a function here, and you expect that it does what they say. This program calculates the sum of numbers. All right, so we are actually contracted by OHK to design a better language. They asked us, so in our experience, how would we change EVM if we want to fix it? Because everybody complains about EVM, including ourselves. For us, it's a major pain to verify smart contracts because of the way EVM was designed. And since we complained, they asked us, how would you change it? How would you make it better? And I said, I would replace it completely. I would use LLVM instead. And they said, why don't you design an LLVM then, virtual machine, for smart contracts? And we started doing that. And it looks like this, which is LLVM. This is the same program that does the same thing, but in an LLVM-like syntax. But it turned out that despite of our huge desire to make LLVM work, there were some things in LLVM that were really not needed for smart contracts, and some things that were missing. So we had to change it. And in the end, we called it differently. We called it Yele. But think of it as a version of LLVM for smart contracts. And for me, what is really important, and not only for me, but also for people in our company, is that nobody ever wanted or even thought about implementing a C++ interpreter. Right? So the performance was, actually the performance of KEVM is comparable to the performance of the C++ implementation, so why even bother? So it was completely designed using semantics. All right, and there are several other languages that we're also defining using in the blockchain domain that we're also defining using K. For example, Michelson, we started recently working with Tezos to define formalized Michelson, and it's quite a nice experience. Again, the performance is, sometimes actually the performance of the automatic integrated interpreter surprises. We work with a company, maybe I'm not even allowed to say the name, I don't know, Dapper Labs, anyway, I have it here now. So they have a language flow based on linear types, with resources and so on, and they have a Go interpreter, an ad hoc interpreter, and we define the semantics of the language, and it turned out that on their test we were 4 times faster. We're still wondering why they found some inefficiencies in their interpreter. So actually this is realistic. We can define languages this way. That's my point, at least in the blockchain space. And I know this is interesting, but maybe I should stop here. Because the next step would be, so many people in the blockchain domain are very serious about the correctness of everything. And we were asked frequently, why should we trust K? Why should we trust your proofs? And my answer is that you shouldn't, because K has bugs like anything else. And now there is a real need for generating correctness certificates. And in fact, since everything K does, I'll just tell you in words what happens. Since everything K does, in the end, can be seen as search for a proof, then what we want is to instrument all these tools to generate actual proof objects that can be checked by a separate proof checker. And the proof checker is really very small. And then we realize that once we do that, once you have that checker, you can have a whole blockchain powered by that checker. You don't even need to have virtual machines anymore in the blockchains. You can have a blockchain that only has one program that executes, a proof checker. Okay? And I would love to talk about that, but I don't think I have time. Let me show you just some picture to see how it looks, if it works, when it works. All right, here it is. So you can have definitions, which can be like language semantics. The language semantics themselves can be on the blockchain. You may want to write properties in programs in any programming language. So what is a programming language? It's a definition, right? You must have it somewhere, stored and recorded and so on the blockchain. And you can make claims, which can be correctness claim. This program does this, or this program computes that. And these claims need to be trusted somehow. Currently, the blockchain validators re-execute the code. That's the trust. That's pretty expensive. So what we'd like instead is to be able to generate proof objects and present proof objects to the blockchain, which has a proof checker. Proof checking, by the way, is super fast. For Hilbert-style proof checking, you can do it embarrassingly parallel. Right? So an embarrassingly parallel process. You can check each step in parallel with all the others. So it's harder to generate the proof object, but once you have it, it's very fast to check. And then claims become truths, so you can color them on the blockchain, or you can trust them. They have been checked once and for all. You don't ever need to rerun the proof. Okay? It's been recorded once and for all. And we have to think about how to incentivize people to do proofs, pay them, basically. And with that, I would like to conclude that the proof checker is the only program that needs to be executed on such a blockchain, and that this can be done. Thank you.
So we'll take a few questions since we anyway started a bit late. Let me also mention that you're also able to ask questions on Slido. So if you go to POPL 2020 on Slido, there is a CPP room, and you can also ask questions there. At this point, no one knew, so no one asked. But it will be an option for the talks coming up.
You mentioned that it still takes several months to verify each new contract. How much of that is developing your methods and tools at the same time versus what you expect to be true in steady state?
More than half fixing bugs and developing our tools, unfortunately.
But do you still think it might be routine to take a month to verify each contract?
I think we'll get to 2 or 3 days eventually, because if you have better tool support, better error messages, then you focus on the actual problem.
Mm-hmm.
I also hope that in the meanwhile, people will, move away from EVM. EVM is not meant for verification. It's very heavy.
One thing I saw missing from that diagram is proving properties about the semantics of the language itself. The most obvious example I can think of would be type soundness.
Yes.
Given that a lot of the verification you've been talking about for K has been about reachability, is this a fundamental thing that K can't do very well, or do you think it can be extended to do that in the future?
Actually, we used to have a Coq backend for K and also an Isabelle backend for K, but those are not maintained. The students, so that happened in the academic, in my lab at the university. Students were interested in that. They implemented it with an older version of K. They used it, and they proved soundness of type systems, for example, in Coq then, after the translation. But then there wasn't really a business case for these tools to be maintained in the company. So they are a bit old. Somebody, I think you also asked about that, right? So we'd be very glad to provide all our support and help. If somebody else wants to bring these tools back to life. But that would be our approach right now. Now in matching logic itself, whether we can do such proofs, you see, so a type system for us is just yet another theory. We have defined many type systems actually using also matching logic theories. So you have two theories and you have to prove a property about these two theories. K doesn't provide any support for that. So the logic, yes, but not K.
Have you done any work on verified concurrent programs using this?
Yes, we did. Actually, this all path reachability is what we have not done in K yet is to add any optimizations for reducing the state space. But actually, K is inherently concurrent. You have to do artificial things to make it sequential. So because all the rules apply concurrently, they match concurrently, and the implementation of the interpreter actually can be concurrent. It's not yet, but there is a push to make it concurrent. So in K, you have to do artificial things to make it sequential. So it's concurrent. The drawback of that is that whenever you prove a property, we have to go through all possible paths, and you can have an explosion there. So we need to have some compositionality optimizations, which we don't yet. So again, the same answer. In the logic, yes, there is no problem. In K itself, we still do exhaustive search. K has a command, K-search, an exhaustive search. And you can detect data races, deadlocks in programs using that command in small programs. Again, smart contracts are deterministic. There was not any business case for that.
I had a question about the compiler portion. Is it that K is able to generate for a language definition a compiler to say LLVM, or is it that, or perhaps both, if you have any two definitions of languages, it can extract a translator between the two? So currently we only generate an interpreter, right? So from a language semantic, I generate an interpreter, and that interpreter will take a program and run it, right? We don't do anything specific to that program. We have a prototype. You see there is also a compiler box here. So I'll talk about this. There is also a compiler box where we do partial evaluation based on the semantics. We take the program and evaluate it symbolically with the semantics. And I actually had some slides, but I had to remove them with that prototype. So basically, what we get is the following. From a semantics of a programming language and the program, I get another semantics, which is the original semantics, partially evaluated with that program. And now I use the normal interpreter. I generate an interpreter from that semantics now, which is specific for a program. And that semantics for your program looks almost like a control flow graph, where you have the states of your program, and the arrows are rewrite rules in the semantics. Do you think that you can reach parity performance with conventional compilers with that approach, or? I don't know. I don't want to make big claims, but I don't want to make big claims in that respect. But I firmly believe, personally, and this is purely personal opinion, is that we should not implement compilers as humans by hand. I think we should generate them automatically from the semantics. It's only a temporary step in our evolution that we still implement compilers.
And I'm sorry, my best friend Vikram Adve, he developed LLVM. So, but you know.
So another framework where you give the definition of a language and it gives you some sort of reasoning framework is Iris, right?
Yes.
In Iris, you give a small step operational semantics and you get a program logic out of it. Now, as far as I can see, the big difference is what you have, the matching logic seems to be sort of some weird form of first order logic, right?
With
Whereas
with least fixed points.
with least fixed points, but it's still very first ordery, right?
Yes.
Whereas in Iris, the fact that it's not first order logic is absolutely crucial, as far as I understand, to being able to do modular reasoning, right? And doing modular reasoning seems to be quite important, because if you have, let's say, a lock, right? If you don't know what it's locking, then you need to sort of describe,
Yeah.
quantify what it might be locking, right? So how would you specify and verify these kind of things, or more generally, fine-grained current data structures in K?
I think that's a long discussion, because things are not always immediately obvious or always immediately what they seem to be, right? So it is known even that first order logic has represented things, that are higher order in principle. So you can still represent them in first order logic. You can also look at models, depend what models you pick. You work with Henkel models, you work with conventional models. And even in higher order logics, once you have a proof system that you use and you find it good enough for everything you do, you can most likely find an equivalent first order logic theory with least fixed points where you can translate all those proofs in it, right? But I know what you mean.
It might be infinitely painful to use, and in general it is.
Yes, you may have finite theories, nice finite theories that may need to become infinite, even proper, not only figuratively. That's also, you may need to work with schemas. But yes, I see your point. Your point is that you may take an argument that has lots of properties, and a higher order in a higher order universe it will be very elegant actually to do that. So again, we were driven by need here. The properties we proved so far didn't need that, and but we define dependent type systems. We define the pure type systems in matching logic as well. So we are looking into that. It's not that we are not interested in that. We are looking into it, but we try to find a nice, clean way to do it. Actually, in K, you can define higher order languages and type systems and prove certain properties about them.
Okay, so maybe we should take the rest of this offline. Are there any more
So
questions?
but I still want to make this point that I'm not claiming that we have an answer to everything, right? I'm just claiming that we have this belief, and we go follow it, see where it breaks.
So if there are no more questions, let's thank Grigore again.